This work presents a novel multi-rotor perching trajectory generation framework for powerlines that avoids collisions with them and maximizes the visibility of the objective power line during the perching maneuver. To enable continuous inspection of power lines without human intervention, multi-rotor robots must be able to perch on the power lines to recharge their batteries during flight. This can usually be done by simply approaching the lines from above, but there are many times where it may not be possible. Quadrotors with agile perching capabilities should be able to perch on the lines in many different angles and use the best choice for each situation. These agile trajectories are computed with a nonlinear optimization problem that includes an efficient formulation of the power line collision avoidance and also of the visibility of the objective power line. The resulting cost function and constraints take the quadrotor to a desired perching pose at a zero or specific velocity while avoiding collisions with the power lines and maximizing the visibility of the objective line during the maneuver. The problem can be solved on board the quadrotor in a matter of seconds before the trajectory begins. The same optimization can be used to compute a recovery trajectory that takes the robot to a safe state in the event that the perching is not performed successfully. To efficiently represent the perching problem, we model the power lines as sets of segments and the quadrotor as an ellipsoid volume. This way, the distance between a quadrotor and a segment can be modeled in a closed form. However, this formula works by assuming infinite length lines, which can end up restricting an important fraction of free space. To solve this, we add an additional term so the collision with the segment is only modeled in its surrounding area. In addition to collision avoidance, we are interested in keeping the objective power line segment in sight during the perching maneuver. This is useful whenever the robot needs a visual feedback of the line to perform control or state estimation. To do so, we formulate the objective line in the robot's camera coordinates and minimize its distance to the center of the image. Additionally, we formulate two constraints to ensure that the segment is centered in front of the installed camera and that the segment is contained within the image. We analyze the performance of the system in two different sets of experiments. First, we test the proposed mathematical modeling without using the perching trajectory generator. The modeling is tested inside an onboard nonlinear model predictive controller that is used to perform inspection flights near a set of power lines. The quadrotor follows a simple waypoint-based trajectory and adapts its height and yaw angle to keep the middle power line centered in its field of view, while also avoiding two potential collisions with them. Next, we analyze the effect of perception awareness in power line perching. The same perching maneuver is shown in both videos, but considering perception awareness in the above case. Both trajectories result in the same perching state, but the perception aware case is able to keep the power line within the quadrotor's camera view until the end of the maneuver. Finally, we show that our framework is also able to work for extreme maneuvers such as perching upside down. The quadrotor is able to reach the perching pose at zero velocity, where a specific gripper or mechanism could be used to perch at the power line. Since there is no mounted mechanism, the system safely returns to a hover position. This work was a joint research effort between the GRVC Robotics Lab from the University of Sevilla and the Robotics and Perception Group from the University of Zurich. Thank you for watching.